Hey guys, it's Miss Johnson and I'm here to bring you our notes for Unit 6, Lesson 4. Today we're talking about how to solve binomial distribution word problems. Really, what we're doing today is a lot of the same of what we have done the last 3 or 4 days now. It's just that we're going to practice pulling the pieces of information that we need out of the context of a question. So if we're given a situation, we need to make sure that we can pick out all the parts that we need. The parts that we would need would be that n, what's x, and is it an equal to, or greater than or equal to, or less than or equal to, or things like that. What's our p-value? Okay, so we're gonna practice just reading through some word problems here and pulling out those key pieces of information. But then really it's all the same. We're just going to look at, follow our chart and find the information that we need. So in number 1, it says, on average, 20% of the bolts produced by a machine in a factory are faulty. Samples of 10 bolts are to be selected at random each day. Each bolt will be selected and replaced in the set of bolts which have been produced on that day. Calculate the probability that 2 bolts or less will be faulty. Okay, 2 bolts or less. So here are the things that we need. I see this 20%. That's going to be my p-value. So that tells me that 20% of the bolts are faulty on each day. So that's a p-value of 0.2 because I need to take that percent and turn it into a decimal. I know that the sample that I'm looking at is a sample size of 10. So my n is equal to 10. Then in part A, it says calculate the probability that 2 bolts or less. That means that I am looking at x is less than or equal to 2. That's the x value there. So now I'm going to go to my table. So get your table out and see if you can find the 10 box. The 10 box is... I'm scrolling on my computer here because I don't have a paper copy with me, so I am looking at it on my computer. So the 10 box, it looks like it's the bottom of the third page or second page, bottom of the second page, and I want to go over to that column where 0.2 is my probability, and then I'm looking at 2 and 1 and 0, so that's going to be 0.302 plus 0.268 plus 0.107. I want to take those 3 and add them up. So go ahead and grab your calculators if you don't have it already. 0.302 plus 0.268 plus 0.107. So 0.677 is the probability there that 2 bolts or less will be faulty. Then the question is find the expected value in the standard deviation of the number of bolts in A. Sorry, that's supposed to have a space there. In a sample which will not be faulty. That makes things a little bit trickier. So if 20% is the probability that they are faulty, think of the fact that 80% is the probability that they are not faulty. So this not in there is going to change the probability that we're looking at. We're not looking at the 0.2 as our success. We're looking at the 0.8 this time. The other thing that I want to remind you of is the fact that this says expected value. Expected value is really just a fancy way of saying mean. They mean the same thing. It's kind of like an average. What do you expect the average to be? All right, so for our mean here, we're going to look at the n. If you don't remember this formula, mean is n times p. So for here, I want 10 times 0.8. So that means 8 bolts is our expected value there. For the standard deviation, again, if you don't remember that equation, it's the square root of n times p times q, which that q value comes from 1 minus p. So in this case, that's going to be 10 times 0.8 times 0.2. 0.2 comes from the 1 minus p. So 1 minus 0.8 is going to give me 0.2. So I need to take those 3 things, multiply them in my calculator, and then take the square root. 10 times 0.8 times 0.2 gives me 1.6. And then I take the square root of that. I do second square root, second answer. I just like doing that on my calculator so that I know I don't lose any accuracy there. So my standard deviation is going to be 1.26 volts. All right. Let's take a look at the next example. It says a crossword puzzle is published in the New York Times each day of the week except Sunday. Suppose Mr. Picard is able to complete, on average, 80% of the crossword puzzles. Find the expected value, there's that phrase again, and standard deviation of the number of completed crosswords he completes in a given week. So the mean here, so let's pick out our key information. If I know that a crossword puzzle is published each day of the week except Sunday, that's a key piece. I know there's 7 days in a week. I'm going to take Sunday out. That means that n is going to be equal to 6. There's 6 crossword puzzles in a week. The other thing that I can see in here is that he successfully completes 80% of the crossword puzzles. So that's my p-value. P-value is going to be 0.8. All right, so down here and in the mean, my mean is going to be 6 times 0.8, which is 4.8 puzzles. And again, you can get out your calculator if you need to and type that all in. Over in the standard deviation, I'm going to have 6 times the 0.8, which is my p, and then times the 0.2, which is going to be my q. And again, that q value comes from 1 minus p. So 1 minus 0.8 gives me the 0.2. All right, so I type those 3 things in. 6 times, this one I am going to use my calculator for, times 0.8 times 0.2. I take the square root of that, and I get 0.98 roughly. My standard deviation there is going to be 0.98 puzzles. So he completes about 5 puzzles, give or take 1 puzzle. That's kind of what that piece is saying. Find the probability that Mr. Picard will complete at least 5 in a given week. At least 5 means that my x value is going to be greater than or equal to 5. If there are only 6 puzzles total, that means that I want the 5 plus the 6. So I need to go down to that 6 box. The 6 box is on the front page. I'm going to go over to my 0.8 column, almost all the way to the right. And I want the 5 and the 6. The 5 and the 6 here are going to be 0.393 plus 0. Is that a 262? Yep, 262. Bust out your chart with me and follow along. See if you can find these 2 numbers that I have right here and make sure that you're finding the same things that I'm finding so that you know you're reading the chart the right way. So I'm looking at the 6 box, the 0.8 column, and I want options 5 and 6 for my numbers of successes. So put those two things together, 0.393 plus 0.262, and I get 0.655 for a probability there. All right, and then the last piece of this question says, given that he completes, it's a good piece there. Remember our conditional probability back from Unit 4. So given that he completes the puzzle on Monday, find the probability that he will complete at least 4 the rest of the week. So given that he completes the puzzle on Monday means that I take that puzzle out. If you think back to our conditional probability unit in Unit 4, that's where we talked about how when you use the word given, that changes your total. That's when we would change that number of cards in the denominator of our fraction, or we'd change the number of total people that we were looking at depending on what the given condition is. So that still applies here. What they're saying is that given that Monday already happened, I need to take Monday out of the equation. So now I have a new n that is equal to 5 because I'm taking Monday out of the equation. And I want to look for at least 4, which means that my x is going to be greater than or equal to 4. Now the p-value doesn't change. His probability is still the same of completing each one independently of the next because those probabilities are independent of each other. They don't rely on the other one. So anyways, this keyword given, if you don't remember that back from Unit 4, this keyword given means that it changes our total. We used to be looking at 6 puzzles. Now we're only looking at 5. So if I find the probability that he will complete at least 4 in the next week, now I need to jump up to that 5 box on the front side of your table, your binomial table. I'm looking at the 0.8 column still, and now I'm looking at 4 and 5. So the 2 numbers that I see are 0.410 plus 0.328. And again, bust out your chart with me if you don't have it and make sure that you're seeing what I'm seeing. Go ahead and look for that. I'm looking at the 5 box the 0.8 column, and then I want x is greater than or equal to 4, which means I'm looking at 4 and 5 together. When I add these two, I add the 0.410 and the 0.328, I get 0.738. All right, let's take a look at our next example. In example 3, it says a study indicates that 5% of American teenagers have tattoos. You randomly sample 10 teenagers. All right, so the things we need to know there. We need to know that 5% is my probability. P equals 0.05. Don't forget to move your decimal point twice. It goes 2 places back. We are randomly selecting 10 teenagers, so my N is going to equal 10. All right, what is the likelihood that exactly 3 will have a tattoo? That's x equals 3. So let's go back down to that 10 box. We were there earlier. Let's go back down. For me, I'm scrolling. For you, you're probably flipping through the paper. So I'm in the 10 box. It's the bottom of the second page. I am going to go over to the 0.05 probability column, and I'm looking at x equals 3. So my p-value there is going to be 0.010. That's where I'm at. What is the likelihood that at least 3 will have a tattoo? So now I want x is greater than or equal to 3. That means I'm looking at 3 all the way up to 10. 3 plus 4 plus ... all the way up to 10. So if I look at that column and I add all the way up there, now the fortunate thing is we've got a whole lot of zeros. So I'm going to add that 0.010 that I had up above, and then the next one down is 0.001, and then everything else is zeros. So it's not going to make a difference. I don't need to add the rest of those. And remember, the rest of the facts are still true. We know that those are rounded to zeros, but we're not going to get caught up in that because since they've rounded to zeros, we're going to treat them as zeros. So I'm just adding those two things together, and I end up with 0.011 for probability there. And then what is the likelihood that at most 3 will have a tattoo? At most. So that means I want x is less than or equal to 3. I'm still including the 3 here. Since I'm still including the 3, I can't do 1 minus. So be careful with that because I'm still including part of what's in part B. So now I'm still in the same box, x equals 10. I'm sorry, n equals 10. My probability is 0.05. That's the second column over. And then I want at most 3. So I want 0 plus 1 plus 2 plus 3. This is going to be 0 plus 1 plus 2 plus 3. So I've got 0.599 plus 0.315 plus 0.075 plus 0.010. So go ahead and add all those up in your calculator. I'm going to type them into mine. 0.599 plus 0.315 plus 0.075 plus 0.010. I get 0.999 there, which is consistent with the fact that the only thing... 0.999. Sorry, I missed a 9 there that I needed. The only thing that's left that I did not include is this. The only thing I didn't include was the thing that was at x equals 4. So if I'm only taking out 1/1000th, that means that I have 999 thousandths left. All right, so let's take a look at this example. It says in example 4, the ABC company manufactures toy robots. About 1 toy robot per 100 does not work. 1 per 100 does not work. You purchase 15 ABC toy robots. What is the probability that exactly 4 do not work? All right, so a couple of things are really easy to see here. I can see that my N is going to equal 15 because I'm purchasing 15 toy robots. I can also see that my X is going to equal 4. The probability is one that you kind of have to figure out on your own. So probability, you're told that 1 out of 100 do not work. So type or list that out as a fraction and turn that into a decimal to get into the right column on your chart. So 1 out of 100 is going to be the same thing as 0.01. So now I'm going to go to my 15 box. It's the very last box in this table. So it's on the back page. And I'm going over to that 0.01 column, which is the very first column, and I'm looking at x is equal to 4. And check it out. That's a probability of 0. So you have a very, very small chance of 4 out of 15 toys not working when the overall probability is 0.01. That's what that's saying there is. And again, it rounds to 0. That doesn't mean it's exactly 0. It just means that it rounds to 0. So the probability of that happening was so small that it rounded itself to 0. All right, one more example. Let's take a look at our last one. So this is one where we have kind of a tree that we're looking at here, a tree diagram, and we just want to highlight how these different scenarios can come into play. It says you sell sandwiches, 70% of people choose chicken and the rest choose pork. What is the probability of selling 2 chicken sandwiches and to the next 3 customers? So we drew a tree diagram for you here where you've got customer number 1 in this first tree, then customer number 2 in this second tree, and then customer number 3 in this third tree. So the point that we want you to see here is that there's a couple of different ways that this could happen. You could have a 0.7 because you're looking for 2 chicken and 1 pork. Okay, so that means you could have a chicken and then a chicken and then a pork. That's where this one comes from. You could also have a chicken and then a pork and then a chicken. That's where this one comes from. And you could have a pork, but then a chicken and a chicken. That's where this one comes from. So this becomes a binomial experiment. It's a little bit different than what we've been looking at with our chart, but it becomes a binomial experiment because there are only 2 choices and they're independent of each other. What the person ahead of you picks for a sandwich has no bearing on what you pick for a sandwich. So that's what's happening there. So when you take those probabilities and you multiply them together, it goes back to kind of our independent probabilities that we learned about back in Unit 3. I would take the 0.7 times the 0.7 times the 0.3, and I get 0.147. I get the 0.7 times the 0.3 times the 0.7, I get 0.147 again. Same thing, 0.3, 0.7, 0.7, 0.147. I'm going to take those 3 and add them up. So all 3 of those things are successes for me in this binomial experiment. I have 0.147 plus 0.147 again plus 0.147 again. Or in other words, 0.147 times 3. So your probability here is 0.441. All right, so that takes us to the end of our notes for today. Thanks for listening and tuning in, and I will catch you guys next time. We got one more lesson left in Unit 6, and then we'll be moving on. All right, thanks for joining me.